Hi, it is time for another physics review problem. I know this is your favorite. So this is problem number 4, and the problem starts like this. A rock weighing 680.5 kilograms is resting on the driveway. A husband and wife tried to move the rock with chains. Mu s is equal to 0.15, coefficient of static friction, and mu k is equal to 0.011, coefficient of kinetic friction. Husband pulls at 45-degree angle from the direction that the rock is moved. Wife pulls at a 15-degree angle from the direction that the rock is moved. And this is the drawing showing that direction of pull. The rock moves only in the x direction, amazingly. What is the tension in both chains? Part A says to list the finds and the givens. So here are the givens. We have mass. You need to list these also. Mass, mu s, mu k, theta for the husband, and theta for the wife. And then I've already given you the drawing that shows those angles in the assignment, but you should draw them too. And then find what is the tension in both of the chains. Normally you would use T for tension, and then I put a sub H for husband, and WI for wife. But the nomenclature is going to get a little tricky when we do trig, so I went ahead and just used H and WI like this. Now notice we've done a problem like this before. It was with a mule. Remember the mule, the two farmers and the mule? So I want you to refer to the December 6th homework. And then the second part of the problem, I want you to refer to the January 11th homework. And I gave you those answers. So if you wanted to get those out and just set them to the side so you know what I'm talking about, you can. Part B says to draw a free body diagram. So it should look like this. Part C says to draw two trigonometry triangles, one for each angle, and label each. So the first thing you're going to need to do is pull out the trigonometry reference sheets that I gave you to put into your binder. Let's look at those very quickly. I've always found this sheet to be super helpful. I've referred to it many times over the years. I always kept it in my desk at work. So after we've looked at those diagrams, we can draw our two triangles, and they should look like this. Notice that HY is vertical and HX is horizontal. And then we have the WY and the WX. And I drew those based on our free body diagram, the direction that the husband and the wife were pulling. D says to add the resolved forces to the free body diagram as open vectors. I like to use open vectors for my resolved forces, so there's no confusion that these are resolved from the other forces. So that should look like this. Where HY is in the vertical of H, and we have hx. Then we have wy and wx. It's a resolved force based on this. So in our imaginary free body diagram, which is what the resolved forces diagram is, H disappears and Wi disappears, and we're left with those open arrow vectors. Let's go back to that reference sheet and decide which equations, trigonometry equations, are going to be the most useful to calculate out hy and hx. So hy is opposite the angle, hx is adjacent to the angle, and h would be the hypotenuse. So let's look and see which of the equations involve the angle and the hx and h, which would be adjacent over hypotenuse. Once we've done that, we need to look and see which of the equations involve the hy, which is the opposite side, and the hypotenuse. So now that you've done that, you can see that we're going to use cosine to calculate out hx. We write it out like this. And then we rearrange the problem, right, to get h all by itself. And our new equation looks like this. Hx equals h cosine the angle that the husband was pulling, which is 45 degrees. And the one for hy looks very similar. So I need you to write down this equation, and this equation. Let's look at this triangle for the wife. It's the same thing, right? It's the same thing except we have a different angle. So the equation look the same. We have a different angle, 15, and we're using the variable for the wife's force. Those two sets of equations are actually our answers for E and F. E says list the equations to calculate hx and wix. from the trigonometry triangles and use the reference sheets, which we just did. And F says, if the rock only moves in the x direction, what do HY and WIY have to equal? Write the equation for the forces in the y direction. List the trigonometry equations for HY and WIY and substitute into this. So we just listed the trigonometry equations for HY and WIY in the previous step. First, though, it said, if the rock moves only in the x direction, which was part of our problem, what do HY and WIY have to equal? So let's look at the free body diagram. And what do you notice about HY and YY? They're the only forces in the y direction, so they have to equal each other. So we can set those equal to each other on our sheet. And you need to do that for step F. You need to write HY equals WIY. What does HY equal? We know that from this trig function. So we write that underneath there. Then we write equals, and instead of writing equals WIY, we write equals the equation that WIY equals. Right here. So that should, do you understand that? G says the husband and wife are just about to overcome the static frictional force needed to move the rock. So what is the nomenclature for that? It's lowercase f sub s, right? You're just about to overcome that. Write the equation for the forces in the x direction. So let's look at that free body diagram again. Where we only had a lowercase f, now we need to write lowercase f sub s for static friction. Write the equation for the forces in the x direction. Well, we know the forces in the f. We know those forces. What is Fs equal to? Mu s multiplied by force normal. Okay, so the next thing we need to know is, what is force normal? We know this. We've done this before. Force normal equals W, right? And what does W equal? Mass times acceleration due to gravity. We're not putting numbers in yet. We're just manipulating equations. Half of physics is manipulating equations. All right, let's look at a typical free body diagram. That's big F minus little f, right? Yes. So if we apply that to our situation, what are the forces then that are working opposite of F? Look at our free body diagram. It's the forces of tension on the rock, tension of the chain that go this way. We resolve those forces in the x direction. So these two arrows have to equal this arrow as long as the rock is not budging, right? That strain to get that rock moving, those forces have to equal until suddenly, boom, they're able to move the rock. I'm going to skip H and go to J, because J says draw a free body diagram in the Z and X direction. Z points up perpendicular to the ground. And the reason we are doing that is because in our in a 2D drawing, we're looking down, right? The 2D drawing looks down and we have X and Y. That's on the ground. And now I want you to draw the same thing, instead of looking down, like we did with the mule being pulled by the two farmers, I want us to look to the side, okay? The last part of the problem is H. Solve the problem. Use correct sig figs. We need to do that. So our first step is to calculate out force normal, which is equal to W, which is equal to mg. So what is our mass? Our mass is 680.5 kilograms. We have to multiply that by G. So you multiply it by 9.810 and you come up with this answer. The next step is to multiply or to calculate out the frictional force due to static. So that's easy. We need mu-s. We need Fn. We just calculated out Fn. Look up mu-s, put that into the equation, and do that math. And then I'll show you my answer. F is equal to lowercase fs, which we already know that because of the free body diagram. So this is where we get to do some nifty substituting. Let me show you that on the screen. Then we end up with our answer, which is H is equal to 3.0 times 10 to the 2 newtons. Make sure that you have your units in the problem.